Welcome to the second day of the course of Advanced Topics, which is brought to you by SINS Project. And also on the web pages of SINS Projects, you will find the recording of this talk, so you can go to again if you enjoyed. And also yesterday, I got some positive response that people very much enjoyed the day one. So let's see, and let's look forward to day two of the Suneel talk. And Suneel, the floor is yours.
Thank you, Ian. Good morning, welcome back. So continuing with the topic broadly themed as in situ microscopy, today I'll talk about the in situ electron microscopy techniques for understanding silicon nanowire growth kinetics and also the nanomechanics of ceramic materials. And the way I have outlined this talk, and before I go into the talk, let me see if I can get the slides. So again, all of this work is, I'm extremely thankful to the Air Force Office of Scientific Research, who has funded my research over the years. And I've also benefited from other funding agencies who have supported my research throughout my career. And in this particular talk, I'm going to be presenting results that are done while I was a postdoc at IBM T.J. Watson Research Center. And my advisor there was Francis Ross, who is now a faculty at the MIT. And the staff scientist there is Dr. Jerry Tursoff. He was an invited speaker at the ICNT 2 years ago. And he is the wonderful theorist that I've ever come across. And if you happen to have any experimental data related to kinetics, he's the person to talk to. He's simply amazing. And his approach to solving problem is very simple. And the insights he provides into any type of phenomena related to crystal growth, nucleation, and other aspects, his depth is impressive in a variety of topics. And the more recently, we have started doing nanomechanical studies, and to that, I'm really thankful to Dr. Jeff Wheeler at ETH Zurich, and I'll present some of the results done in his lab. Okay, so in this talk, first I will go over a rather elementary introduction to nanowires. And then I will present some of the results from our in situ transmission electron microscopy studies aimed at understanding the kinetics of nucleation and growth of primarily silicon and germanium nanowires. And in the second half of the talk, I will present some of our more recent results obtained using scanning electron microscope as a tool to observe and to quantify the mechanical behavior of highly refractory carbides. And these are very high temperature, hard materials. Okay. And again, a note about the references. Most of the references are taken from relatively old literature. And so they may not reflect current state of the art. And I know that SATEC and BUT folks have worked on nanowires, and it's not intentional if I've left out any or all of the references. Okay, so this introductory portion of the slides are all aimed at people who have not heard of one-dimensional nanowires. I know that they're not that old, but it's been already 20 years since the first studies of nanowires in the recent era have been published. And so I'll quickly go through what they are and what are their potential applications in one slide, basically. And then I'll come to the synthesis aspects. Okay, so you may have heard of nanowires, quantum wires, pillars, whiskers, and if you're old, then you may even heard of terms called anisotropic crystals. And so basically, these are all highly anisotropic crystals, meaning that anything that doesn't have a spherical shape are all anisotropic. And typically, all crystals are at room temperature or moderately low temperatures are going to have anisotropic shapes. And the shape that one crystal assumes depends on thermodynamics and the way it is synthesized. And depending on the crystals that are grown under the conditions that have been grown, you can observe these shapes at nanometer scale and all the way up to meter scales. Okay, so here is one example. These are not necessarily wires, but these are crystals of ice that form when you have really cold environment, like it seems to be here now in some parts of Europe. And if you're also familiar, I'm sure you are, with stalactites and stalagmites, these are also anisotropic crystals that grow from solution phase, and some of them grow from the bottom and some of them grow from the top. And it depends on the kinetics that control and the way the source is supplied to make these materials grow. And the nanowires in the recent 20 years of literature typically refers to structures that are tens of nanometers long and anywhere between hundreds of nanometers and longer. And there are a couple of aspects. So there are what I call freestanding nanowires and substrate supported nanowires. And so the nanowires have been produced in the powder form or in solution form. And after being produced in solution, they're dried and you obtain these freestanding structures. And you also can have substrate supported nanowires, which can be in plane or out of plane. And here is one example of what were called as nanowires. This was a few years ago. And these are silicide nanowires made of rare earth elements. So this is dysprosium silicide. And this is a scanning tunneling microscopy image showing the growth of these silicide in plane. And these are one-dimensional structures. These are out-of-plane nanowires. These are silicon nanowires grown on a silicon substrate, and these are sticking out of in the Z direction. And these are atomic wires or quantum chains, if you will. So these are literally few atom wide chains. And again, this is a scanning tunneling microscopy image. This is a higher resolution image of the same thing, showing these gold atom chains on a highly vicinal silicon surface. And these tend to assemble along these step edges and form these highly anisotropic structures. Okay, and in the nanowire community, there is another term that is used, and this is nanopillars. These are no different from nanowires. It's just the way they're fabricated. Typically, they're made either by top-down etching or by synthesis without the use of any external catalyst, typically in templated surfaces using chemical vapor deposition. And here is a scanning electron microscopy image showing the lithographically patterned and grown indium gallium arsenide nanopillars. And if you're old enough, you may also have heard of the term called whiskers. And so these are no different from nanowires. It's just that their dimensions are different. And typically their widths are microns in width. And the lengths can be millimeters. And typically these were used in the field emission applications. And these have been grown by the same techniques that are now I'm going to be talking about using vapor phase synthesis. And whiskers are common. They are observed everywhere. And here is one example of nickel sulfide whiskers that are geologically, it's available or found in nature. They're found on the moon. So these are iron sulfide or iron whiskers with sulfur tips, or that's obtained on the moon and in the mines as well. So these are germanium disulfide. Nanowires or whiskers, if you will. And if you see, there is these little branches that are growing outside as well. And so these are very common, these nanowires and whiskers and nanopillars and quantum wires. It's possible to grow them. It's very easy. And in the last 20 years or late 1990s, there was a interest that was regenerated and they were coined the term nano and at that time, and they're referred to as nanowires. And the interest comes about because people were tired of carbon nanotubes, and nanowires had similar dimensions. And one of the advantages that the nanowires offered is the ability to synthesize structures with chemical abruptness. So you could go from a p-type structure to an n-type, which was not possible with carbon nanotubes. And so this ability to change chemistry, composition, and structure within that one dimension offered numerous possibilities. And also by changing the size of these materials, one can invoke quantum confinement effects, and there was that possibility of opening up new properties and hence new applications. In terms of architectures, it's limited by your imagination. For example, you can make these structures of single element, of a compound, multiple compounds, alloys, anything that you can think of, and with different diameters, different morphologies, or different crystallinities as well. So you could make single crystal, you could make twinned, you can make it a controlled twins or uncontrolled defect stacking falls inside the structures. And this is to show that you can change the composition within the nanowire in the axial direction. And you can also change it. So in here, you have this superlattice style structure where you have the segments of the different material B that is embedded in as quantum dots, or you could have materials grown as junctions. And so you could have, hypothetically, you can have a semiconductor of one type and another semiconductor here, or you could have a metal insulator semiconductor, or whatever possibilities that you can imagine. You can synthesize them. And you can make even, just like axial structures, you can make core shell and multi-core shell heterostructures are also possible. Okay. And here is one example that's from the Lund University group, Kimberly Dick's group, that had shown that you can grow these branches by sequential seeding of the catalyst. And most of these wires are grown using a catalyst, and I'll come to that in a few minutes. And you can add another catalyst and grow these branch structures as well. And you can also do controllable growth of these axial heterostructures where you can have silicon, germanium, superlattice nanowires. And you can have quantum dots of one material embedded within another material. So these are group 3,5 compounds with indium phosphide, I believe indium phosphide quantum dots with an indium arsenide or vice versa. And here is rather complex material system. So here you have indium arsenide at the bottom and gallium antimonide at the top. So completely different, although they're all group 3 and 5 compounds. You have 4 different elements in here. Nevertheless, you can grow them as axial heterostructures. It's not easy with some of these elements and some of these compounds, but nevertheless, it's possible. And here are other interesting structures where you can use a combination of bottom-up synthesis. So you can do chemical vapor deposition and deposit a solid structure. And you can locally, chemically etch to create these hollow shells within these core shell structure. And so in this particular example, this is a gallium phosphide, gallium arsenide, gallium phosphide core shell structure. You can selectively etch one of them, and then you can end up with these concentric ring structures. And here is another elegant example where, and this is done by the Eric Bakker's group in Netherlands. They grew gallium phosphide, and then they coated it, they covered it with silicon. And under the right conditions, you can end up with hexagonal structured silicon. And you etch away the gallium phosphide, and you end up with these thin shells of silicon with hexagonal symmetry. Okay? So you can also create these metastable structures using one-dimensional crystals as templates. Okay, and in terms of applications, there are numerous applications, and there are tons and tons of papers published on this. I'm just going to focus on a few, mainly to say that these properties can be different from that of the bulk. So here is one of the early papers, and this was on a silicon carbide nano pillar, and they showed that the mechanical properties can be different from that of the bulk, and that it increases the strength of these pillars, increases with decreasing size. And now it's pretty much common, and it has routinely observed now the size dependent change in the strength of a variety of materials. And here is another example for silicon nanowires. that the size of the nanowire affects the electron or the charge carrier mobility in this material. So these are all nanowires of different diameters, and you see here the mobility of the holes, and it changes. And here is another example of how the properties change with defects. And these are photoluminescence data acquired from two types of indium phosphide nanowires. One of them is a single crystal without any structural defects, and the other one is highly twinned structure. And these are power-dependent changes in the photoluminescence spectra, and you see that the behavior is opposite in these cases. And here is another example to show that the surface morphology of the nanowires can affect the thermoelectric efficiency. And this was shown for silicon nanowires, that as you increase the surface roughness, then its thermoelectric efficiency was significantly higher. And so all these were to say that you can have very interesting nanowire properties, and they depend on the size, they depend on the composition, crystallinity, and surface morphology. And all these are at your own disposal, so you can take advantage of each of these to create a given application of interest. And I've put in only a few applications here. There are a variety of devices that have been made using a wide variety of nanowires. So I encourage you to look up the literature if you're really interested in making nanowire-based devices. The most common are nanoelectronics and optoelectronics, and to some extent as power generators, but a common theme is also to use them as sensors because they have these high surface area. Okay, now let's move to the main topic, and that is how are these materials synthesized? And one of the key requirements for any of these structures to be made is that these are one-dimensional. So you need to have the growth along the axial direction to be significantly higher than in the other two directions. And so one has to identify the processes that give rise to the growth or accumulation of the material, preferentially at the top or at the bottom ends of this material rather than in the radial direction. And traditionally, and one of the first methods that has been identified for giving rise to the growth of nanowires is the so-called vapor liquid solid process, where the catalyst, and I put it in quotes because it's not always that this material serves as in the strictest definition of a catalyst. Nevertheless, it serves as a getter for the depositing species. And if it is a liquid, the process is referred to as vapor liquid solid process. And I'll go into the details of this in the next slide. Or you can have vapor solid solid process where the catalyst is a solid, or you could have direct simple vapor phase deposition without any catalyst. And you have other approaches of making nanowires or nanopillars where you use an advantage of a template or compositionally or chemically different surface. And so you could have oxide or no oxide, and that can promote the growth in 1D. Okay, so now let me come to the most commonly used technique that is referred to as vapor liquid solid process. And the literature dates back to 1960s, but there are papers even before this that have observed nanowire growth, but they were not referred to as the VLS grown nanowires, because at that time there was significant debate on how these materials would form in this one-dimensional structure. A variety of materials have been grown. Elemental materials, semiconductors, metals, compounds, oxides, nitrides, carbides, pretty much any material that you can think of can be grown in the form of nanowires with the right kind of catalyst. Classically, for silicon nanowires to grow, if this is what I'm going to be focusing on in the next following 10 slides or so, the most commonly used material that is used as the catalyst or catalyst forming material is gold. And you introduce, and the idea is that you choose the material that forms a low melting eutectic with the incoming material that is being deposited as the nanowire. And under the right conditions, this incoming material alloys with the metal of interest and forms a liquid. And this liquid acts as the preferential sink for the depositing material, which can then diffuse through the droplet or at the droplet, around the droplet, and gets deposited under the droplet. And so because the vapor is used as the source, you have the B, and because the catalyst is a liquid or the liquid alloy, and that's the L, and the solid that you form is the crystal that grows. And so that's how you have the VLS process. And in this process, the diameter of the nanowire that you obtain is controlled by the size of the catalyst, and the length is dictated by the growth time or the growth flux and the temperature. And gold seems to work well for a variety of materials to be grown as nanowires via VLS process. And it has been used in the literature mainly because it's inert and you can deposit it in one chamber and transfer it to another reactor and do your nanowire growth. And although here I've written as it's a good catalyst for dissociation, it's not necessary for it to be a catalyst. If it forms a liquid that permits the incoming material to diffuse to the bottom of the liquid or to the substrate, then that is good enough to grow the nanowires. And one of the things for people that are interested in doing nanowires or any materials is that the phase diagrams can often help identify the right candidates that can help form the right alloy for a given approach, a given process. So if we take the silicon nanowires that we are interested in growing and using gold as a catalyst, this is a binary phase diagram that shows that with about 18% of silicon, you form a low melting eutectic. So gold melts at 1084 degrees Celsius. Silicon melts at 1414 degrees Celsius. But this particular alloy melts at about 360 degrees Celsius. Okay. So anything above this temperature and with more than this amount of silicon, you can then grow silicon nanowires. And hypothetically, let's say that we chose a deposition temperature of around 500 or 525. And if you continue adding silicon, you're basically walking along this line. And so initially you form a gold silicon alloy, and you will have a mixture of solid and liquid. Once it crosses this eutectic composition, you will have completely a single phase liquid gold silicon alloy. And as you continue to add more silicon, the excess silicon precipitates out, and under the right conditions, you get the nanowire. So here is and our approach for all these experiments that we have done. We typically deposit a thin film by evaporation of gold on a single crystal silicon substrate. And once you anneal it, it alloys with the substrate silicon, forms the alloy, liquid droplet. As we start introducing precursor in our experiments, it was disilane, but there are a variety of silicon precursors that one can use. You can induce the nanowire growth. So this is the bright field transmission electron microscopy movies. This is done in plan view, where you have gold crystals initially, and then now the disilane was introduced, and you start seeing the droplet formation and eventually the nucleation and growth of crystals here. This is done in what is called as reflection mode geometry. And so the substrate is placed in line, and I'll show you a schematic of how the sample is placed. And then in this mode, you can observe the nanowires to grow out of plane. Okay. Now let me go into the details of this process. And before I proceed to describe how these materials and what are the factors that control the growth, I just want to point out that slight variation of the VLS process is the vapor solid process, where the catalyst remains as a solid. And in this case, typically the growth rates are slower than what you expect with a VLS process, because the material diffusion through or the dissociation ability of the vapor precursor can be different compared to that on solid. And here is one example of such a solid catalyst leading to the growth of a silicon nanowire. So this is a silicon single crystal nanowire growing with, in this case, gold aluminum alloy with silicon. And under this temperature, this is a solid catalyst. And so you can see that it's heavily, strongly faceted tip. And as you have seen here, it also grows, but relatively slowly compared to the droplets that are in the background in this particular field of view. Okay, so now let me come to the details of how these nanowires grow and how electron microscopy can help quantify the observed phenomena. So you have seen this video before. Let me play it to you again. So initially, this is in ultra high vacuum, and it's solid gold catalyst, pure gold catalyst. Now we introduce disilane, and immediately it starts forming liquid droplets. And as the disilane is continued, you start seeing this nucleation of this lighter contrast material, and that is silicon. So schematically, we start with pure gold. And once we start introducing disilane, the silicon from the disilane gets absorbed by the gold, forms the alloy. And as the alloy gets supersaturated, you start seeing the nucleation and growth of silicon crystals. And all these are done in plan view, and that's why these images look as shown. And in terms of if you were to walk through the phase diagram, initially, we start out with solid gold, and we keep adding silicon. And eventually, we end up with a single phase alloy liquid, and that is gold silicon liquid. And as you continue adding more disilane, there is more silicon coming in, and you start nucleating. So you have this liquid droplet with a solid silicon crystal. And if we consider the steps involved in this process, there is a time that is required for the silicon to be deposited onto the solid gold, and for a time that's involved. Even if it's shorter, it still needs to alloy diffuse and form a homogeneous alloy. And eventually, it needs to be supersaturated before you form the excess silicon comes out in the form of silicon crystal. And so this total time required from starting from pure gold to the time, the very instant that we observe this nucleation, is what we're going to refer to as incubation time. When we plot the incubation time from the images that are acquired at any given temperature and pressure, you see that it increases with the size of the gold particle or the gold silicon alloy droplet. More importantly, if you follow the evolution of a given droplet from the onset of this crystal nucleation and the growth of it, the plot here shows the radius or the size of this silicon crystal as a function of time. And you see that initially there is no change or no growth, and that's because this is the incubation time, the time required for the solid gold to become liquid gold silicon alloy and start nucleating the silicon. And as I mentioned in the previous plot, this incubation time increases with increasing size, and these blue, red, and green curves correspond to different size droplets. And in all these experiments, and as you can see here, there is a crossover. There is a drastic increase in the size of the silicon crystal, followed by a crossover, after which there is a slower increase in the size of the crystal. So this is due to the instantaneous nucleation of the crystal, followed by slower growth of the crystal. And so this point of crossover is a measure of the critical supersaturation of silicon in these droplets, and we can quantify this. And it turns out that for gold silicon alloys, the amount of silicon supersaturation increases with increasing temperature, and which you would expect. As you increase the temperature, the solubility increases as well. And the most often thermodynamically, you don't expect to have any supersaturation, because right after it crosses the liquidus line, you should expect to see crystal formation. But in always there is a nucleation barrier. And so to overcome the nucleation barrier, then the crystal, there is a supersaturation is a consequence of that. Okay, now I'm going to show you the nanowire growth kinetics. And for this, what we have done is, or what Francis came up with, is to place a bulk single crystal of silicon in such a way that the electron beam direction is in line with the face of the crystal. And so if when the nanowires grow out of the crystal, we can view them in transmission mode. And I must emphasize that all these experiments were done in what I'm going to call as IBM TEM, because this is rather old. It's from early 1990s. It's a 300 kV Lab 6 filament TEM, but the key aspect of it is that it's ultra high vacuum. Okay. And to my knowledge, there are very few ultra high vacuum TEMs that are currently operating in the world. And towards the end of the talk, I'll make one comment about it. But in my opinion, this is essential to be able to observe phenomena and to be able to interpret the observations, because there are more and more experiments that are being done in a conventional TEM. And when you don't know what is in the background, then whatever you observe is subject to misinterpretation. Let me skip this one and come directly to one of the aspects. So in terms of nanowire growth, as I mentioned before, the key requirement if we want to have a nanowire is that the growth rate needs to be higher axially compared to radial growth. And in terms of what contributes to whether the material grows axially or radially, depends on the amount of material being deposited directly at the tip of the wire versus on the side walls of the wire. And there are factors contributing to both of these depositions is the diffusion of material either through the droplet or on the surface of the nanowire. And all of these can contribute to how fast a nanowire grows and how does it exhibit the size-dependent changes in the nanowire growth rates. And so here is a summary of how the nanowire growth would change with the size of the wire and what you should expect to see. If the Gibbs-Thompson effect that I mentioned in the last lecture plays a role, meaning the vapor pressure associated with a given droplet, which again increases exponentially with the curvature of the droplet. If that is influential in the growth, then the larger diameter nanowires will grow faster. And that is because the larger the diameter, the curvature is smaller, which means there is lower vapor pressure associated with the larger droplet compared to the incoming flux. And so the concentration gradient is higher here. And that's why the larger diameter nanowire grows faster than a smaller diameter nanowire. If the diffusion through the droplet plays any role in how fast the nanowires grow, then the bulk droplets or the larger diameter droplets, it takes longer time to diffuse through, and hence the smaller diameter wires are expected to grow faster. And a similar observation can also happen if the diffusion of molecules or atoms that are deposited elsewhere to come and get collected at the tip of these nanowires. So if surface diffusion plays a role, and that is typically the case for group 3-5 compound semiconductor nanowire growth, where the surface diffusion and collection at the tip influences the growth rates, there you would expect to see the smaller diameter wires to grow faster. If none of these factors are contributing significantly to the nanowire growth, if these are all fast, diffusion either through the bulk or if there's no Gibbs-Thompson effect, then the growth rates are solely controlled by the incoming flux. And in that case, irrespective of the diameter, all the nanowires grow at the same rate. In our experiments, and the reason that I emphasize in our experiments is because depending on the precursor that you use and depending on the pressures that you work with, and the temperature ranges you work with, you may observe different growth kinetics. For silicon nanowires grown in the ultra-high vacuum system using fairly low pressures of silicon, we observe that the growth rate is fairly independent of the diameter of the nanowires. And it increases with flux, so basically it's flux-limited growth. And the activation barrier associated with this type of growth is around half an EV, which is significantly lower than the energy required for dissociation of disilane, indicating that the gold silicon droplets promote the deposition of silicon from disilane. Okay, now let me focus on a few interesting aspects that would not have been observed if not for the TEM. So what you're looking at is two silicon nanowires. These are growing in the 1-1-1 direction. One of them has a smaller droplet and it's a smaller diameter wire. This has a larger droplet. This is gold silicon droplets. What you will notice is as time progresses and there is constant deposition going on, so there is disilane being provided, this droplet is decreasing in size. And eventually this droplet disappears, at which point the nanowire stops growing. Okay. And it turns out that this process is a consequence of Ostwald ripening happening on top of the droplets. So here is experimental data. This is for 3 different wires with droplets labeled A, B, and C. And here is the volume of the droplets plotted as a function of time. And what you see is that volume of droplet C is increasing, whereas the volume of droplet B decreases after a certain time. And the volume of droplet A increases initially and decreases eventually. So all these are classic example and signature of ripening. And so what is happening is that when you have an ensemble of nanowires of different diameters, these gold droplets basically see each other even though they are situated on top of the nanowires. And so the same phenomena that I talked about in the last lecture happens here. The gold diffuses down the nanowires and reattaches to the larger diameter wires. So the larger diameter droplets get bigger with increasing time, and the smaller droplet diameters decrease with time, and eventually they disappear. Those that do not have any droplets, they stop the vertical growth because now it's direct simple vapor solid deposition, and so those growth rates are significantly smaller. And what you have noticed here is that as the droplet is increasing or changing in size, there is a concomitant change in the size of the wire as well. So this leads to tapering that you observe in the nanowires. You can take advantage of this, and this is one such example where the nanowires were grown for a certain time and annealed without any growth. So the growth was stopped and just heated and let the size of the droplets change. And then if you resume the growth, those droplets that have gotten bigger would grow with a larger diameter, and those droplets that got smaller would grow with the smaller diameter wires. And one of the neat things that you can do is, because you have ultra-high vacuum environment, you can intentionally change the gas composition. And in this case, we introduce oxygen. And the reason for this study at the time was that this Ostwald ripening phenomena was not observed by most of the community that were growing silicon nanowires. And it turns out that a very little amount of oxygen can help suppress Ostwald ripening. And here is an example. So initially, the wire is growing in clean environment. And after a certain time, a little bit of oxygen was introduced into the system, and the growth was continued. And you see that the volume of the droplet was decreasing in ultra-high vacuum. But once you introduce oxygen, the volume of the droplet remains fairly stable and the growth continues. An unintended consequence of the introduction of oxygen is that the wires tend to grow now along 1-1-0 direction, whereas without any oxygen, you get primarily 1-1-1 oriented nanowires. So you can take advantage of this effect, and so you can switch on and off oxygen and you can change the orientation of the wire. And so in principle, you can get these zigzag style nanowires. Okay, now let me give a slightly different flavor for germanium nanowires. And back then, there was a lot of literature on what temperature is required to grow germanium nanowires. And as I mentioned before, the idea was that nanowires grow with gold as a catalyst via VLS process, meaning there's a liquid. But some of these experiments showed that the nanowires grew at temperatures below the eutectic point for that particular alloy. And so the question was whether the germanium nanowires, they were grown at temperatures even as low as 100 K below the eutectic temperature, eutectic point for gold germanium. And so the question was, is the catalyst a solid or a liquid? And it turns out that you can grow germanium nanowires both with a liquid droplet and using a solid catalyst as well. So you can have VLS process or VSS process, but the growth rate is significantly different. It's 100 times faster with the liquid droplets as the catalyst rather than a solid catalyst, solid 10 times faster. And here is an example of an experiment that we did where initially there is digermane, which is the source of germanium. And we decrease the digermane pressure, and you see that this smaller diameter droplet became a solid. I'll show it to you here again for this one, that also would have become a solid. You see, so by changing the pressure of digermane, this catalyst changed its state from liquid phase to solid phase at the same temperature. Okay. So even though, and there is this question of always whether we believe this temperature or not, and the question, and you do not have to trust this value. The only thing that is proof that we have a liquid is that you have this smoothly curved surface and you don't see any diffraction pattern from this one. So we know that it's a liquid, irrespective of what this value is. But after a certain time, you see that this particular nanowire has become a solid. So on the same substrate and nearby nanowires, one of them, the catalyst state changes just by changing the germanium flux. Okay. And here is more data to see what happens when we change the pressure. And this is an experiment where the digermane pressure was changed with time. And we measured the size, the shape of the droplet. So the lateral diameter, if you will, of the droplet and the height of the droplet. And you see that there is this oscillatory behavior as we change the pressure of the droplet, saying that either the composition of the droplet is changing and or the shape of the droplet is changing as you change the digermane flux. And here is an experiment where we did this, where we changed the pressure and we watched the growth of the nanowire. So initially there is high amount of digermane. And as you drop the digermane flux, watch what happens at the edges of the nanowire. It starts faceting and it forms these highly corrugated surface. And once you increase the pressure back up, it resumes this normal growth again. So we interpret this spontaneous facet formation as a leaking of germanium from the droplet. So basically, the droplet is initially supersaturated with germanium. And as you decrease the pressure, the excess germanium comes out of the droplet, and that excess germanium is deposited on the side walls. Okay. And so our hypothesis is that the droplet has excess germanium that facilitates formation of a liquid phase even below the eutectic point. And as you change the digermane flux, and this supersaturated gold germanium droplet is only stable as long as you have a steady supply of germanium. Once you stop the germanium flux, this excess germanium comes out of the droplet and then it becomes a solid phase. Okay, so those results are basically to show you what are all the factors that can control the nanowire morphology and microstructure. And here I'm going to summarize some information more than what I have presented in my talk so far. And I did not talk about the catalyst composition per se, but we have done experiments where we changed from pure gold as the metal to gold aluminum, and that can change how the nanowire grows. And gold aluminum silicon ternary alloy droplets tend to be more stable against Oswald ripening than just gold silicon droplets. And depending on the chemistry of the catalyst, you can have different rates of incorporation of the material. So some alloys are better as catalyst for dissociative chemisorption of the precursors compared to the others. And the catalyst composition also affects the wetting angle. So the shape of the droplet on top of the nanowires changes, and that affects the nanowire morphology itself. And of course, as you change the composition of the catalyst, you can change the composition of the wire, which is particularly the case for group 3,5 nanowires. And catalyst stability, so we have done experiments where when we change the temperature during the growth of nanowires, the droplet on top of the nanowires becomes unstable. At mild changes in temperature, it tends to oscillate. But if you change drastically the temperature, the droplet can fall off the top of the wire, at which point you lose the growth of nanowire. And in terms of the growth parameters, the temperature, the flux, and the relative partial pressures of precursors, which is common for group 3,5 semiconductor nanowire growth, all these parameters can affect the wire diameter. For example, if you change the temperature, if you increase the temperature, the solubility of the alloying element changes. And as a result, the wetting angle also changes. And then you tend to have larger diameter wires. And the growth orientation can also change, as I mentioned, about the effect of oxygen. And the shape of the wire depends on how much material is being deposited axially versus radially. And so you can have tapered shapes that can happen as a result of these change in parameters. In terms of the challenges and the future, there's a lot of possibilities for nanowires. And in fact, the recent trend is to combine one-dimensional structures with two-dimensional layered materials. And the idea would be that you have a 2D layer wrapped around 1D nanowires. And also within nanowires, creation of these quantum dots is a very attractive process. And in principle, you can assemble 2D layers in the form of nanowires as well. So for example, gallium selenide is a layered material, but you can grow them as nanowires. And so you can have a nanowire made of 2D layers. And the other attractive aspect in right conditions is you can change the composition of the 2D layer axially. So you can grow nanowires of 2D layers with different compositions. In terms of challenges, it's always been the case, and it's still the case, is that if you were to compete with silicon microelectronics industry, you need to be able to grow ultra-thin silicon nanowires. When I say ultra-thin, sub 10 nanometer diameter wires, there are some experimental approaches where you grow a nanowire and you oxidize radially. And so you can reduce the size of the nanowire, but to be able to grow them and pack them side by side I think is still a challenge. And it's definitely the case for these group 3,5 nanowires. So there are those aspects it may not be possible to address them. Then there are possibilities or opportunities for finding a different set of applications for these nanowires. And as I mentioned before, in terms of in situ TM experiments, all I showed here was the growth of nanowires, but it has been used for a variety of observations. For example, you can do electrochemistry within a TEM. You can do catalysis inside a TEM. And it's great. You can observe phase transformations, as I mentioned, from going from solid state to liquid state, so melting and freezing of alloys, and finding you can construct or reconstruct phase diagram for nanocrystalline materials. And in some ways, it's complementary to the LEEM technique for two-dimensional or for surfaces, because in TEM, you're essentially probing the bulk microstructure of a given material, even though it's thinned down. And in terms of challenges, typically you need to identify the right material or the right sample geometry that works best. So for nanowires, Francis came up with this reflection geometry that helped us use bulk single crystal to watch the nanowire growth. But if you were to choose a thin film or a thin cross section, and if they're made using focused ion beam milling, then you end up with gallium contamination, which can lead to gallium surface segregation during heating, which we did observe. And this is an unintentional consequence of using focused ion beam milling. And you may have other elements diffuse as well. So when you use platinum to glue the fib-made sample to the grid, you can have platinum diffuse through the grid onto the sample, which we also observed. And these are undesirable if your real goal is to just focus on the sample of interest. And so identifying the right approach for making the sample is a key, and it's a really difficult aspect, because most TEMs are not designed to be in ultra high vacuum. And so you're working with an environment with unknown gas composition. And if you plan to study oxidation or reduction or phase transformations, you're at the mercy of the residual gas chemistry. And even though you may observe very interesting phenomena, you cannot quantify it. However, there is a lot of papers that are published using a regular conventional TEM for in situ microscopy. And people have heated their samples and observed melting of nanowires or phase changes, and it's getting published. And I have some issues with it. I don't think it's right, because you don't know the chemistry of the gases, which means you don't know what is happening to your material during your observations. And ideally, it will be really nice to have an ultra high vacuum TEM, but I understand that there are costs associated with it. At the minimum, one should quantify the gas composition, and if possible, change the gas composition during your experiments to see how it influences the observations. And I was happy to learn that here at SciTech, you have an excellent suite of SEMs that enable you to do both environmental or high pressure studies and also in ultra high vacuum environment. Okay, now moving on to the next topic, and that is on the nanomechanics of transition metal carbides. So in the next 30 minutes or so, I'll showcase how in situ electron microscopy can be used to study mechanical behavior of materials. And motivation for this study arises from the fact that the transition metal carbides have a variety of applications, but I wanted to share with you one paper that I found during my research on this refractory carbides, is the plasticity in purely ionic crystals. So these are sodium chloride structure materials, magnesium oxide, potassium chloride, and these are optical micrographs obtained a long time ago. And these are manually bent at room temperature. So these are bulk crystals, nothing nano about them. I believe these are millimeter size crystals. And these just bent. And typically, conventionally, at least, it was thought that ionic crystals are not as plastic as metals. Okay? And so observing plastic deformation is not common in these types of crystals where the strong ionic bonding. But back then, the same authors suggested that this is something that is common and should be expected in cubic ionic crystals. And transition metal carbides, they are more metallic than ionic, and they have a mixture of bonding. And so it's plausible that if ionic crystals of the same crystal structure can show plasticity, then even transition metal carbides may exhibit bulk plasticity. And that's the hope. And I'm glad that I was able to work with a variety of collaborators and co-workers who helped do these experiments in the TEM and also in the SEM. And the materials of interest for those of you that are not familiar, these transition metal carbides, along with borides and nitrides, are used in advanced structural applications. Some of the applications include space shuttles and for rocket nozzles where high temperatures, these materials are required to be stable and survive high temperatures in highly oxidizing environments. And so these extreme conditions where conventional superalloys do not survive. And that's where these borides and carbides come into play, because they have exceptional high temperature strength compared to any refractory metals. And among these class of materials, cubic carbides have been shown to be or found to be interesting because they have a mixture of metallic, ionic, and covalent bonding. And they behave like metals when it comes to electrical and thermal conductivities. And they behave like ceramics when it, in terms of its strength, hardness, and stiffness. Okay, so it's a nice blend of metallic character and ceramic properties, and that make them very attractive for a variety of applications. In terms of its melting points and mechanical properties, transition metal carbides stand out among all other types of materials. In fact, the hafnium carbide and tantalum carbide alloys are supposed to have the highest melting points among all types of materials. And even basically all these group 4 and 5 carbides, they have really high melting points. And one thing to be said is that their properties are sensitive to the carbon vacancies in them, which can affect their hardnesses. Nevertheless, all these materials are significantly harder than conventional metals, and also they're very stiff. They have very high elastic moduli. And they're generally believed to be brittle when subjected to tensile stresses at lower temperatures. And all the existing literature until recently have been done on high temperature mechanical behavior. So this is for single crystals of zirconium carbide of 3 different orientations. And this is the stress at which they exhibit plastic deformation as a function of temperature. And the data says that these have fairly similar properties irrespective of the orientation. And these crystals were subjected to compression at these temperatures, but there was no room temperature data until recently. And however, there was very interesting papers published a long time ago that showed that there can be localized plasticity even at liquid nitrogen temperatures in these carbides, and that there may be a change in the slip system in these materials at these low temperatures. So, which is interesting given that these materials are supposed to be significantly hard at room temperature. Okay, so our hypothesis was that, well, it's maybe these transition metal carbides are not brittle to start with, but all the papers that I've reported on brittleness may have to do with bulk defects that may be present in them that lead to the premature failure of these materials. If that's the case, if we were to make really pristine crystals, then we should be able to observe plastic deformation in them. And so to do that, we started out with bulk single crystals, and we make them into smaller crystals and try to do compression tests. And so I'm going to present to you an overview of the type of measurements we did with the compression of single crystals of zirconium carbide, tantalum carbide, and both in the TEM and in the SEM, and of different orientations, and in the SEM also at different temperatures. Okay. And to be able to do these experiments, so it's a brute force approach. We start with a bulk crystal, and using focused ion beam milling for almost a day, you can make these structures and then make these really small pillars. So these are sub-micrometer wide pillars. And now these structures are ready for TEM experiments. So then we load it into a pico-indenter, which has a transducer in it, inbuilt into it. And so we can do mechanical compression and observe at the same time. And so we collect the data and be able to analyze its microstructure during the deformation. So here is a bright field transmission electron microscopy movie acquired during compression of a 111 single crystal of zirconium carbide. And this is the diamond platen that is compressing the pillar. And this is the stress displacement curve that's obtained during this compression behavior. You may have seen some dark contours that are moving down the wire, and that is the essentially dislocation network propagating through the crystal. Okay. But what you can noticeably see is that there is this, initially there is a linear change in the stress versus displacement, followed by a transition to a non-linear change in the behavior. And this transition is indicative of the onset of plastic deformation. There is no abrupt catastrophic failure, meaning that there is no fracture. And so this pillar basically deforms plastically. And this is a similar type of experiment done with 100 oriented single crystal zirconium carbide. And notice that now you'll start forming these slip. So there is macro scale shearing that occurs, and you can capture them during both in the images and also in your stress displacement curves, where you observe these little pop-ins, and that happens as the slip events occur. Nevertheless, the crystal stays, meaning that there is no fracture of the crystal. Okay. So in one case, you observe this formation of these macro scale shear, and in the other case, you just see only dislocation network forming. And this is orientation dependent differences in the mechanical behavior. And we can quantify this size, the stress and the displacement curves. And so these are obtained for 5 different sizes, from all the way from 100 nanometers up to about half a micron size. And each of the colors represent these different sizes. And from these types of stress displacement curves, we can extract yield strengths of and yield strength is defined as the point of transition from elastic deformation to plastic deformation. And this yield strength, if we plot it as a function of size, we see very interesting behavior. For 111 oriented crystals, there is a rather significant change in the size dependence of this yield strength. Whereas for 100 crystals, it's rather not so much. And this size dependent change in the strength of the materials is being well documented, mostly for metallic crystals. And even for ceramic and ionic crystals, there is a considerable amount of data that says that as you decrease the size, the strength increases. What is surprising here is that this behavior is opposite in terms of the orientation dependence, is opposite to what is expected for sodium chloride structured crystals. So the existing literature for MgO, which is exactly the same structure, same crystal structure as zirconium carbide, but MgO is ionic, the behavior is opposite, where they observed 100 to be softer than 111. And so then we use density functional theory calculations to identify the mechanisms that lead to this type of change in the behavior. And we attribute this to operation of 110 and 100 slip systems in this material. Now, I know I'm rushing through a little bit, but please feel free to ask me questions anytime before, during, or after the talk. And we've done similar experiments for tantalum carbide. And in all these experiments, the single crystal retains its crystallinity after compression tests as well, both in the zirconium carbide and in the tantalum carbide. And from these similar types of stress strain curves, we obtain yield strengths for different sizes and for the two different orientations. And the data is summarized here. And what you see, although there is a large amount of scatter in the data, they basically appear to have the same trend and about the same yield stresses, indicating that 011 oriented crystals and 100 oriented crystals behave mechanically similar irrespective of the size. And we attribute this to the operation of the 111 slip system to be on par with 110 slip system. And if you're not familiar with what is slip, just please let me know, and I'll happy to explain what it is. It's basically, typically in most materials, it's the close packed direction is where you would have the dislocation motion to occur on a close packed planes. But this is a sodium chloride structure, so in here 110 is the most favorable slip plane that is typically expected. Now, but depending on the crystal, depending on the material, even though same crystal structure, you can have a different slip system operating. And this is the surprising aspect that was not known previously. And I'll come back to this more when I'm talking about the higher temperature compression test conducted on tantalum carbide in the SEM. And so these are in situ scanning electron microscopy measurements of uniaxial compression done at room temperature all the way up to 600 degrees Celsius. And this particular set of data is from 300 degrees C. So again, these are diamond pillars, diamond platens that are used to compress, and the sample is maintained at a given temperature. Now, these temperatures, I should indicate that it's very low temperatures for these materials. So tantalum carbide melts around 3000 C. And so the melting point with respect to the homologous melting point, it's only about 10%. And so one does not expect any significant atom motion at these temperatures, and the dislocation mobility also should technically be very limited. But what we see is very interesting. With the changing temperature, so initially at 25 degrees C for 100 crystals, we see one macroscale slip event. And the corresponding curve is shown here by this black curve for the stress strain behavior. But if you see at 300 degrees C, you see significant slip activity. All these shear bands that you see on the surface is a characteristic of plastic deformation. And if you see the green curve here, that's the stress strain behavior for compression of the same crystal orientation, but at a slightly higher temperature, indicating that the plasticity increases with temperature, which is expected, but not for these type of crystals at such low temperatures. And the nice thing about SEM is that you can, without going into the TEM, you can identify the slip systems if you collect the images at the right angles. And so it turns out that for compression of 001 oriented crystals at this temperature, the 110 is the preferred slip events. And so that's the macro scale slip events that you observe. And it's definitely not 111. It's visually, you can see that the 111 plane would intersect the 001 axis at this particular angle, which is different from experimentally observed. And that's the same case for a different pillar as well. But note what happens when you increase the temperature. So this pillar is compressed at 450 degrees Celsius. And here, it turns out that it's not 110 slip system, but we do observe a change in the slip system. And that now you have 111 slip operating at this higher temperature. And our observations are consistent with ab initio molecular dynamics simulations that were done on small scale 100 oriented pillars. And if you plot the data for this pillars compressed, 100 oriented pillars compressed at different temperatures, you see a monotonic decrease in the yield strength with temperature. And if you read a little into this data, you see that there seems to be a change in the slope of the curves from right about around 300 degrees C or so. And we attribute this change in slope to a change in the slip system, that between or below 300 degrees C, you have 110 as the dominant slip plane. And upon increasing the temperature, the most active slip system that contributes to plastic deformation is the 111 slip system. And we find a little more interesting aspects when we did compression of differently oriented crystals. In this panel, I'm adding in the data obtained from an arbitrarily cut crystal. So this is a 310 oriented single crystals of tantalum carbide. And we have done also for 110. And these are the stress strain curves for 3 different crystal orientations at a few different temperatures. What is noticeable is that all these plots are plotted to the same maximum in the yield stress, is that the strength or the point of deformation for the same tantalum carbide is highest for 001 oriented crystals when they're compressed along 001 compared to, and they're lowest for 310 oriented crystals. So 310 oriented crystals are softer under compression compared to 001 oriented crystals at any given temperature. And so to identify what is going on, we again look at the images of these pillars and try to identify the slip systems. And I don't want to bore you with the tables, but these are all the possible slip systems that can be present when you have a 310 oriented crystals. And the ones that I've highlighted are the ones that are most likely slip systems that are expected to operate, given that's where you would have the highest resolved shear stress. And so what you find is that even at room temperature for 310 oriented crystals, the most expected, geometrically expected slip system that to be active is 111, not 110. But experimentally, what we observe is the opposite. We observe the operation of 110 slip system, indicating that the compression, during compression of this material, we do not observe what is known as the Schmidt's law, which tells you that the resolved shear stress and the activation of a given slip system is the one that gives the highest resolved shear stress. Okay? And that seems to be the case for at all different temperatures. The light orange colored lines indicate the slip that we observed, and the blue lines here correspond to the orientation of the slip that is expected. And in all cases, we observe the slip along directions and on planes that are not the ones that are expected from the geometry, indicating that there is an anomalous slip activity in these crystals. So to explain this behavior, we came up with the following. So typically, when you have a crystal that is being either pulled or compressed, the dislocations will move along a given plane of interest. And if that's your slip plane on a given slip direction, you have a normal resolved shear stress. But now, maybe that during compression, the resolved component that leads to the dislocation motion may be countered by a stress that is acting opposite. So this is like a frictional stress that tries to push the planes together or closer. And so this normal stress can suppress dislocation motion. And so we refer to the geometrical factor associated with the orientation for a given slip system by this term P. And we can identify the angles that give rise to this. And without going into all the details here, it's suffice to say that we can explain the experimentally observed orientations and attribute this to the normal stress component. So I didn't want to go too much into the details because I was not sure how much you're engaged in this topic. But I just wanted to share with you these results and to tell you that the in situ microscopy can help observe and understand the nanomechanical behavior. And we have used this approach for studying a relatively not so well-known material system, at least in this community, although the materials itself are fundamentally important for a variety of applications. And we observed quite surprising results that conventionally accepted active slip system is not always active, and it depends on the material. So even within group 4 and 5 crystals, group 5 crystals behave slightly different compared to the group 4 crystals. And within group 5, we observe a highly anomalous slip activity, and which we think is because of this normal stress that contributes during compression of these crystals. With that, I'm going to stop, and I wanted to end significantly before compared to the last lecture. So thank you for your attention, and I'd be happy to take any questions you may have.
Thanks a lot for fascinating talk, and I'm sure that there will be questions. So please ask, either raise your hand, either virtually or turn your camera and do this motion. So you will be given word. If you are like don't want to ask in person, just you can write your question into chat and I will ask in place of you. So maybe I will start. I will select one of my questions because I have a lot of them. So I would like to ask about this change in the direction of the silicon nanowires, because you said that if you introduce oxygen, it will just change the direction of the growth. And why is it changing?
It changes the wetting characteristic of the droplet. And it's just that the droplet changes its position on the tip. And when you look at the tip and in all our images, we tend to visualize the interface between the droplet and the wire as a flat interface. But it so happens that you actually have two 1-1-1 planes at the interface. And so when you add oxygen, it changes its ability to wet the entire wire, and it just shifts to one side of the wire, which would be on the 1-1-0 plane. And so the interface changes.
So it's somehow invisible inside the wires,
right
like
at the
that.
interface, right at the interface.
Okay, so then you just make this motion goes different direction. Okay, so Matthias has a question.
Hi. Yeah,
Hi.
I was wondering about the VLS process a bit more in detail, and I was wondering because you had a very nice explanation, and I wondered how small is the smallest nanowires that one can produce in this manner.
So from the VLS process, using vapor precursors, the smallest nanowires people have produced for silicon is 2 nanometers. But it's possible that the precursor chemistry may have been different. So maybe by using oxygen simultaneously with silicon, you may be able to etch away the excess nanowires. And the key for growing the smaller diameter nanowires is to prevent these droplets from becoming larger by coalescing with the other droplets on the surface. So if you can produce these droplets, let's say in very confined spaces, and also maybe in the vapor phase itself, it is possible to produce smaller diameter wires. And the other requirement is whether that material is stable at that size. So if you take gold and silicon and you make a 2 nanometer alloy, it probably may want to evaporate. It may not want to stay as a liquid. And that may be the case for other low melting, typically for all group 3-5 semiconductors. If you take gold gallium or gold indium, and given that the gallium and indium are low melting metals, when you decrease the size to sub 10 nanometers, you can have size dependent depression playing a role, and it depends on the vapor pressure of those alloys. And so the stability of the droplet is the issue.
Thank you.
Yes.
I have also
So-
one question, if it is possible. For crystal growth, as I understand, we can have rate limited step bulk diffusion or absorption at the surface, so-called surface reaction. Is it possible to switch from diffusion control crystal growth to surface control crystal growth?
Hypothetically, I would think yes. So
Yeah.
if you increase the temperature, or you mean in the same system without even changing
Yeah,
the
I mean,
catalyst?
it's a complex question. The same system, because of course everything depends. It depends on the nature of materials, depends also on the direction. But it's really a very interesting question. The bulk diffusion, this is one case,
Yeah.
and surface reaction, I mean, adsorption at the surface could be also the limited step.
So
of course, there is no option to have both. We should take one or another one, and it will be pretty nice to control to switch from one to another rate limiting steps. Is it possible or not in practice?
I would think so. So typically when you have a liquid droplet, the bulk diffusion is fast. But if you, let's say, intentionally you reduce the temperature and you have a solid catalyst, then the diffusion through the solid catalyst is going to be a dominant factor. And so in the same system, by changing the temperature, now you eliminate that to be the limiting step if you make the catalyst liquid. And then you could have surface diffusion limiting the growth.
So we can play using the state of matter. I mean,
state of the catalyst.
From solid, for example, to liquid. When we play in this direction, we can control. Yeah, pretty nice answer. Okay, thank you. Yeah, it's really cool. Yeah.
So thanks for your questions. There's some other people. So I will ask my second question. So you mentioned the leaking of, I think it was germanium, out of the nanowires when you remove the gas. So why it happens? Because you just changed the...
Right. So what we think is happening is that when we do the growth at temperatures below the eutectic point, you have more germanium than the solubility expected at that temperature for that alloy. So you have gold germanium alloy with excess germanium in the droplet, and it's metastable, and its stability depends sensitively on the amount of germanium pumped into the droplet. So if you have a constant supply of germanium into the droplet, it stays happy, it stays as liquid, and you continue the growth vertically. Now, once you remove this excess germanium flux, this droplet is not stable with that much excess germanium, so that excess germanium leaves the droplet. And if with sufficient amount of germanium lost, the droplet becomes a solid. And that's what I was showing in one experiment. In the other experiment, if you don't give enough time for all the germanium to be lost, but if you keep switching back and forth the pressures, the consequence that you see is that some of the germanium that gets deposited on the walls, that promotes faster growth, because now you have slight changes in the surface morphology, and that enhances the deposition rate. So you basically have a smooth surface versus a rough surface, and on the rougher surface you have higher deposition rate, and that leads to this observed faceting that we saw.
So it means that the droplet is more happy to be super saturated if you still provide the gas in.
Right. If there is germanium being constantly supplied, even though there is a little bit of germanium leaving down, you can still have it. But now when we decrease the germanium flux, the other possibility is that you have hydrogen passivation along the sidewalls of germanium. And now that once that is lost, now there is easy pathway for the germanium to leak down.
Okay, so this is, yes, I understand that. Okay, thank you. Audience? Okay, there is one question in the chat. So,
Silicon growth to increase the thickness of silicon coating layer on the apex of field electron emitter, rather than cleaning the tip and recoating it. Yes. So in normal vapor deposition, you will have a conformal coating. So if you do regular, let's say, assuming that you're using a vapor precursor, such as the silane or disilane, you will get conformal coating on your tip and everywhere, wherever you have a hot surface. And if the tip material is all chemically homogeneous. If you have different chemistry at the tip of the material versus the rest of the tip, then you may have different rates of deposition. But otherwise, you can get a uniform coating. And okay, there can also be complications with the crystal orientation of this tip that is made of, let's say, if made of silicon. Then if you have 111 facets versus 001 facets, you can have different growth rates. So then you may not get conformal thickness.
okay, thanks for the question. I was like, at the beginning, you showed the grow on nanowires from top perspective when you make liquid, and somehow there was like very quick coalescence observed. You know, even it seems that the droplets are far away, and then suddenly they joined together. And how is that?
This is in reference to the nucleation experiment.
It's a nucleation experiment. Because I didn't notice any motion of the droplets.
So it's this one, right?
Yes, this one.
Can you see this video being played?
Yes.
Can you see it? Yeah. Okay. So here, initially, these are all well separated. And now you have silicon being deposited on the grid. And now you see this jumping. Is that what you're referring to?
Yes.
Sudden jumping and absorbing stuff. Yes?
Yes.
So, okay. So it's a plan view membrane. Initially, it's silicon nitride. And the islands are isolated. These gold crystals are isolated from each other. And once we start silicon deposition, even though majority of silicon is being deposited onto the gold crystals, you have some direct deposition of the silicon onto the grid. And that provides an easy pathway for the droplet to diffuse or jump. And that's why you see these sudden jump and coalescence events occurring between seemingly far crystals. So you don't, even if you don't see a slight gray contrast, you could have silicon growth on the membrane.
So is it silicon, or is also gold is coming out to make this enrich this silicon?
That's also possible. It is possible, but I would tend to think it's less likely because gold. So if gold and silicon are given choice, they're likely to be together rather than separate. And so wherever there is silicon, inevitably gold will alloy with it rather than leak out of it. And so it is possible for some of the gold to diffuse from one droplet to the other, just like in the previous case. And that can also contribute to easy pathway.
Thank you. So now you have last chance for your questions. Like during the talk, of course, you have like Suneel is around, so you can approach him, ask him, discuss with him for hours if you wish, and if Suneel would like to do, and just contact him and you can discuss. So
yes.
Thank you very much for your fascinating talk, and we will look forward for other talks in the series. So thanks again. And
thank you. Thank you.